Okay, I'm going to walk through some ways to fix invalidations, inspect and fix invalidations using some of the tools that have been developed relatively recently. I've prepared a first as a starting case, just a very simple demo file, one that contains an opportunity for creating invalidations and looking at them, one that where the code is so simple that we understand it very well. Just a couple of preliminaries. Keep in mind that at the time this video is being filmed, the tools that you need are really only available in the master branch of Julia. So I've taken the, I've already prepared the way by looking, configuring VS Code so that it's using as an executable path my master branch of Julia. I've built this from source. You could download a nightly binary, for example. But of course, sometimes your invalidation hunt ends up leading you into Julia's own base code or its standard libraries. And in those cases, it's good to be using a source build anyway. So you don't have to use a source build, and especially as these tools get out into stable released versions, that's may not be required nearly so often, but for now, that's the recommended approach. So here you can see it. Now I've got a nice easy example prepared. So I'm going to launch a Julia REPL, and my REPL actually loads revise by default whenever it starts up, and so that will be loaded in the background here. And now I'm just going to include this code here, so now we're ready. So we've made these method definitions, we've called them here and that forces compilation of these different methods here, right? And now we're ready to trigger some invalidations, but record them. And so first I'm going to illustrate the most careful way that you can record invalidations, and then we'll just get a little bit less careful in a moment. The most careful way is to load just Snoop compile core. And that's a very minimalistic package that only lets you essentially record the invalidations. And so I'm going to save that to the invalidations to a variable called invs. And the key thing that Snoop compile core loads is this macro Snoop R. And now whatever you put inside of the macro is what any statements or method definitions that you create, it will turn on the ability to record these invalidations. So we're going to define a new method of f. We're going to define float 64 equals 2, and we're going to dump them. Now the output of this is not terribly informative to humans, so I'm going to suppress the output here. Now that we've recorded the invalidations, I'm going to load the full Snoop compile package, and this is what lets you do the analysis. And we can actually look at the list of unique invalidated method instances by this invalidated list. There were 6 items that got invalidated. So that gives you a sense of the scale of how bad it is. But if you're in the business of fixing invalidations, you very quickly want to get to these invalidation trees call. And what this does is this organizes the list of things that were invalidated into a tree structure. And this tree structure, there's going to be one of these trees per method that triggered invalidations. In this case, we only defined one method, so we're going to get at most one of these tree structures. And here you can see a list of what got invalidated. So I'm going to pull out this one item, methinvs. It's an object of type method invalidations defined in Snoop compile equals trees of end. You usually want to start at the end because the thing that had the most impact is usually last. And so then I'm going to pull out the last of these back edges to take a look at in detail at what happened. So root equals methinvs of dot back edges, and that comes from right here. And then the last item is that item 2. I could put 2 or just put end here, right? And you can see that that's indeed this particular method instance here that's described right there. And indeed, it has 2 children as summarized there. But what we can do now, we can look at this in more detail. And so you can see sort of the call chain that got there. If we do min children equals 0, now we can see the complete call chain. But the most powerful tool, and the one that I'm illustrating here, is this ascend tool. And so if we do this ascend, what it's doing is it's starting at the lowest level call and letting us browse upward. So this is an interactive menu. If I use the down arrow on my key, you can see that cursor advances to the next item here. And here's the end of the chain, so hitting the down arrow anymore doesn't do any good. So now I'm sitting here, for instance, at this call here, and if I hit enter, what I'm doing is I'm selecting this one for analysis. This is an illustrative case, because what you can see here is there's a call here, and the type here is marked in red, and that's because it's not a concrete type. And so these calls suggest then that Julia only has partial inference information, and it's not able to be certain of what type of object it's going to be called on here, right? This actually is a concrete type. It's a concrete container of an abstract type, and so that one's not highlighted in red. So we're going to take a look. We're going to inspect this call here. I'm going to hit enter, and you can see now it pulls up another menu. So again, I can use my up and down arrows to select the different items here. And this one only really gives you two explicit options. You can do another thing not shown. You can hit Q to quit. But the two options here are you can look at the source code here. And what is shown here in brackets are the lines of this file here from which the call to the parent occurred. So we're in call F, and it called to the parent, which is F, on line 2. Okay, that's not surprising. We look up here, sure enough, it calls F on that line 2. So this isn't really going to tell us that much, but just to show you what happens, now you can see it actually reopened this file in my editor, and it positioned the cursor on line 2 where the problematic call to F has occurred from. Okay, so that's one of the things that you can do. And sometimes you can fix invalidations just by looking at the line that contained the problematic call. So I generally recommend that you start there. If you can't figure it out from there, then what you want to do is you want to go on to browsing the type inferred code. And so I move my cursor down, I'm going to hit enter, and now we're in this wonderful package called Cthulhu. Okay, and this is a little complicated. If you've never used Cthulhu before, it can take a while to get used to it. I'm going to walk you through it, although Cthulhu has its own documentation. So the idea here is we're looking at the typed code that starts really right below this line here, and we're invoking call F, a particular method with argument types, vector, abstract, or float, and Julia knows that it's going to return an int 64. Okay, now there are two sections to display. The variables section, this lists all of the named variables that are in in the body of that method, and there's basically everything always has a self. It's essentially its own function name, but the only other variable of note is container, which indeed is one of the arguments to this method, right? And it's showing here that this is a vector of abstract float. So that's the list of variables that are relevant in this method. And then here's the body of the method. You can see here that the body is known to return an int 64. And then in yellow is each statement, each line within the source code of that file. Now, this is a very simple method. It's only a single line, so there's only one yellow line here, basically, right? Now, there are two there are two methods, two calls below that, or two statements essentially below that. There's a get index, and that's essentially this statement here that extracts the first element from the container, and then the call to main. And these sort of percent symbols here are essentially, you can think of them as temporary storage within the implementation of the method. So it's going to store the result of this get index to this temporary %1, and then it's calling main.f on that, and it's known to return an int. This is highlighted in red because it deserves special attention. Again, it's not a concrete type, and so you should note this. Okay, and then here's the return statement. All right, so now one of the things that's worth saying is Cthulhu has a lot of options. In particular, note this optimize and warn one. So you only get the red if the warn is on. If the ascend, unlike other methods in Cthulhu, actually by default turns off the optimization. If you turn on the optimization, which I'll do just by hitting O on my keyboard, Now you can see it's a slightly different implementation. It's inlined that call to get index that comes from array.jl, and that turns out it resolves, once it's been inlined, it resolves to array ref, okay? So it's basically the same thing, but we've actually essentially incorporated the body of that method. We can see the same thing. I hit O again to turn off the optimization, so now we're back to base.getIndex. And down here in the lowest sort of section here, you can see the individual function calls, method instance calls, really, that are being made. And again, as a menu, so this little dot is next to the currently selected one, so you can go into there. Now we're actually within the body of this method that's in array.jl. If I hit E for edit the source code on my keyboard, it'll wait a second. Revise has to actually load information about where to go find this from, and it's found it, and sure enough, it's positioned you to the method that we just used here. Okay, so if we're satisfied with what we see there, we can go back by choosing the backward pointing arrow there, and now we're back here. We could go and we could inspect into this call F here, and you can see in this case, since it's got the hash in front of it, there are actually two method instances that could have been called in this circumstance. It doesn't know in advance which of these would be relevant, but in fact, they both point to the same method here. So, you know, going back, whoops, that was in the REPL. Save that. Here we know that it's defined right here in the function. Okay, so this is a circumstance. So basically, all of this was simply to sort of introduce you to the features here. I'm going to hit Q and back out and come back to the command line. And the reason why is that in this artificial example, there's nothing to fix, right? I don't know why the user, you know, has this poorly typed container that might be important. So, you know, there's really nothing I can do to fix this invalidation. So I'm not even going to try. But at least now you, I think, have an introduction to the features. To show you how you might actually go about fixing an invalidation, I think it's useful to have a more real-world example. And so for this example, I'm going to choose the fill arrays package. Keep in mind that by the time you watch this video, it's very likely that the issues that we discover here today will have already been fixed, so you may not be easily able to replicate it, but hopefully at least the type of analysis that we do will be informative. So I'm going to record invalidations and immediately parse to trees. This is a little sloppy because Snoop compile itself might have triggered some invalidations that I'm not going to catch this second time around, but any form of progress is good. It's not necessarily terrible to miss some. So I'm going to just take this quick shortcut and do the invalidation trees. I'm going to do a Snoop R, and now I'm going to say using fill arrays, right? So here we're loading a package while recording invalidations. So any invalidations that happen from that package or any of the packages that it triggers loading of will be recorded. And so now you can see we're getting a much sort of larger output. You can see we're getting a list of 3 of these method invalidation trees. And so one of them is triggered by a new method for any. Another one is triggered by a new method for all. And the final one is triggered for broadcasted. And these are ordered in importance, where the ones that trigger the most invalidations are last, okay? And this is, so here you can see most of these, there's only a few children. This gives you, if you look at the number of children, this gives you a sense of how many different method instances would need to be recompiled. You know, when it's down in the single digits, if you can fix it, that's great, but it's maybe not a huge deal. This is really a big deal, right? There's a ton of methods that are being invalidated through this sort of call chain. And this is really where we should be directing our attention. So I'm going to extract that one, methinds equals trees at the end. And then I'm going to say root equals methinds of back edges of end. And so here we are at this broadcast style type of string, and then on an abstract array, okay? And now let's ascend and see what's up with this, okay? So here we're getting a much, much longer list, right? We can scroll down to the bottom. You can see this downward pointing caret indication that it goes, far beyond. And so we're going deep, it looks like, into the package code, right? So Julia's package standard library. So there's something here which is triggering a problem. When you get these very long lists, sometimes you might want to see, are there lots of methods here? And so here you can fold the menu. So I'm going to hit the space bar, and you can see this plus here. And so you can see, for instance, at this level, there were a couple of different branches in this tree, that both of which were called from download, verify, unpack, but with slightly different argument types. And so, those separate branches there. But if we intercept the problems at an earlier stage, then maybe none of this will be relevant anyway. And so I'm going to unfold it by hitting the space bar again. And so one of the things, when you're faced with a large tree like this, the question is, where do you start? And there's no rule to this. The more you know about the code that you're inspecting, the better off you are in general. But as a kind of a rule of thumb, here's what I typically do. When you see these not concrete argument types, by the time you've lost inference information, it may be a little too late to intervene in a meaningful way. That's not always true. So for example, if you're iterating over the elements of an abstract string, you know that those must be abstract chars, even if Julia's inference engine doesn't always know that. And so sometimes you actually can meaningfully intervene, even at this stage, in a way that at least improves the quality of inference in some fashion. But as a kind of a default, I think a good guess is to start at the first place where all of the argument types are concrete. And so it's this call here to this unpack. You notice the hash and the number here. That's because this is almost surely a keyword argument body method. So it has two regular arguments. This is sort of that self argument that we saw earlier. And then this is probably from a keyword. We'll actually take a look and see if that's true. So I'm going to hit enter and select it. You can again see that it's showing me a menu of choices. I can just look straight at the call to this broadcasted method. So calling string on an abstract array must have happened. And here's kind of a surprise. It's from the logging framework, and it occurred on line 295 of logging.jl. So logging framework is not defined in package. So what the guess would be that unpack actually uses the logging framework, and the problematic call actually occurred from the logging framework. So let's take a look at that. I'm going to hit enter and invoke it. And sure enough, here it's taken to this thing. And this is just simply essentially copying over an argument to the message. If you go and look up, and you can see message is just one of the arguments here. It's not real informative what's going on here. So, this occurs in a macro, or something that's being used to serve one of the macro body methods for the logging framework. So we didn't get a lot out of this. So I'm going to go back down here again, since I'm in VS Code, click on this to activate it, hit my down arrow, and start taking a look at the typed code. And now you can see it's a much bigger output. Don't be too intimidated. Once you've done this once or twice, it's really not that bad. First thing I'd recommend doing is hitting E to edit the method here in VS Code. And now you can see this unpack method. Sure enough, it's a keyword method with a Boolean keyword argument. You can see that it spans several lines of code. And since we already got the clue that it's that broadcast method is being called from logging framework stuff, we could start looking for some of those logging macros. And sure enough, there's an @info here. And sure enough, there's a broadcasted call of string. So that's one way you could find it. Another way you could find it is you could just start looking through here, and if you scroll down through the list of calls here, eventually we should see somewhere, maybe I missed it. Did I miss it? No, it's a little farther down, I guess. Oh yeah, here we go. There's this 80 on this %82. So it's sort of statement 82 in the type inferred code. There's this call to broadcasted with a string acting on an abstract array, returning an object of type any, exactly as we have suspected. So, all right. So let's see about trying to actually fix this problem. So let's scroll up. This is much more complicated. There are many more lines of statement. You can see that these at logging ones, these are come from expanding the macro. And so there are some things that don't, that are in this code that don't appear visibly in the source code here, right? And the problematic call is to this string.symlinks. So that's the variable that's causing us problems. So I'm going to scroll all the way up to the top and see, just double check that in the variable section, indeed symlinks is inferred to be an abstract array, but it doesn't know anything else about it. So let's see where symlinks gets set in the source code. Symlinks, you can see, is being defined here through this call to list tarball symlinks. So we're now off to the races. The first thing to do is to see, why is symlinks poorly inferred, right? This tarball path is one of the, I think, inputs. So that's known to be a string. So the type instability in this case is introduced by this call to symlinks. All right, so we can scroll down and we can look for, or sorry, the creation of symlinks through the call to list tarball symlinks. Okay, so here we can find that call here. It's in this %29. We could have gotten that from roughly the statement corresponding to that line number if we wanted to. And so I'm going to hit enter here and edit and take a look at the source code for this method here. All right, so now, where are we? Well, you can see this is a much shorter method. That's nice. It makes it a little easier to debug. You can see that symlinks is being inferred only as an abstract array. And let's see how it's created. So this is a list comprehension, and it's a list comprehension being created from MM. MM is fully inferred, but you notice that it's a vector of a union element type. So the inner object, the elements of the items within MM, so the M's here, that should be a vector, and the elements of that vector are either nothing or a substring of string, okay? Now, if we take a look at this statement here, we can see that there's really no acknowledgement that the entries in M might be nothing, right? I guess this could conceivably be a nothing, but then this dear name of nothing is not going to succeed, right? That call would fail. And the join path would also fail if that's a nothing. So, there's an implicit assumption in this line of code that the elements of M must actually be abstract strings, okay? So we can fix this then, maybe, let's try it, by putting a condition on this. So this condition would essentially, it's implicitly assumed that all of these are going to actually be matches. And so let's filter out only those things where you really did get a match. So, and we'll submit this pull request, and the package developers will tell us whether or not that is what they wanted to have happen. Maybe they wanted the code to throw an error or something like that, okay? So I might say if M of 1 is not nothing and M of 2 is not equal to nothing. Okay, so now I'm going to hit save. Now the question is, have we fixed this? Well, it's not super easy to tell right now for one reason, and that is that on master, I can't immediately update this thing due to a current issue in VS Code, but I can use revise for that. However, I'm not tracking changes to the package code, so I actually have to exit this, go all the way back to the REPL. I have to say using package. I have to say revise.track package. And now let's try this ascend root again, go back into here, and now let's take a look at the type of symlink. So now it's an array, okay? It's progress. That's better than an abstract array, but we actually haven't quite successfully found the elements of this array. And so element. Why not? I'm not entirely sure why, but maybe we can help out inference. You may remember that this was known to be a substring of a string. Why don't we just force this thing to become a string? So I'm going to wrap this thing here in string. I'm going to save the file, and I'm going to hit revise and see if that actually helps. It doesn't seem to have so far, but for reasons I don't fully understand, sometimes it seems to help and start at the beginning again with Cthulhu. And so now I hit Q to go back and then re-entered it again. And sure enough, take a look at this. Now list tarball symlinks is returning a vector of a pair of a string. So if we look up through the source code here, you can see a lot of the red is gone. We've really, some errors are not, this command is not. That actually turns out to be an interesting artifact that you need to do some initialization of the package before that call can be expected to succeed, and Cthulhu hasn't sort of realized that. But anyway, we've really fixed a lot of the problems with this call just by that one little change we made there. So at this point, what I would probably do is, try rebuilding Julia. And if you're building Julia from scratch, one thing, I'm not going to do it here because I'm not sharing that part of my screen, but if you, instead of like make, you might need to build a custom version, and in that circumstance, you'd want to say that you're getting package from a Git repository, which I had actually set up before getting started on this. So that would be the one final thing, and you could test that. You could go back and look for invalidations, and you'd find out, hooray, we actually have fixed this invalidation. So that's all I have to demonstrate for you today with Snoop Compile and its facilities for helping you track down invalidations. Thanks for watching.